So thank you very much for saving a little time to listen to all the bad news that I'm going to give you. Basically, what I will try to explain this afternoon in France and so this morning so in the US is a kind of summary of the course that I teach at Mines Paris Tech, trying to explain why, if I put it in very simple words, when we try to understand the world through economics, we miss major points. Actually, we miss mostly all the points. And why the kind of party that we have been celebrating for a couple centuries now is going to end, wish it or not, in the coming decades, and what it means for us. Which is basically what I'm going to now. All those that are in a hurry, you can leave. So the question was, will technology save us from climate change? So as you probably know, a book has just been released a couple of days ago that says yes. So again, all those that are in a hurry can leave. Actually, it's not that simple, and I'm going to try to explain why. So we're discussing climate change. Actually, the climate system, the climate system is a big physical machine that takes place on Earth. A big thermodynamic machine, which has been existing for the last 4 billion years, because there has been a climate system on Earth for as long as there has been an atmosphere on Earth, and that is a couple billion years. That climate system has always changed. So we have not induced climate change. The climate system has always changed since we had an atmosphere on Earth. But these changes may take place over durations that vary a lot, depending on the forcing that is the external or internal cause of the climate change. For example, we have a rapid variation of the climate change, so to say, which follows changes that take place into the atmosphere, and which causes the system to change over days. And that's typically the kind of change that the weather forecast is going to explain to you, colder here, hotter there, etc. But there are other causes of changes of the climate system than what can happen in the atmosphere. For example, what you can see here is that over billions of years, actually, the sun has changed. For example, 4 billion years ago, the power of the sun was a couple 10% below the present power. And so the Earth was receiving less energy than the energy it receives today. So that, of course, changed the climate system. Over, let's say, 10,000 to 100,000 years, the orbital parameters of the Earth, sorry, I didn't translate, change. And that's namely due to the fact that the planetary system that orbits around the sun does not comprise only one planet, that is the Earth, but 9 planets, and namely 2 massive planets, Jupiter and Saturn, that exert a kind of attraction, actually not a kind, some attraction on the Earth, and that causes the orbital parameters of the Earth to change over time, change slowly. And that is, for example, what has triggered the ice ages of the Quaternary era. You can have the continental drift that changed the climate. For example, the fact that a continent took place in Antarctica about 30 million years ago slowly cooled the climate because you had a big ice cube that appeared there. The formation of mountains or the change of sea level is also something that can change the climate system. It takes place over very long spans of time. Volcanoes can be a cause of massive climate change. For example, one of the competing hypotheses to explain the collapse of dinosaurs is massive volcano eruptions that took place in the traps of the Deccan about 60 or 70 million years ago. Then you can have, again, interactions between ice caps and the ocean and the atmosphere that can change the climate system. On this time scale, you can have, of course, the change of the greenhouse effect that I'm going to explain in a couple of minutes that can change the climate system. And the greenhouse effect did change before there were humans on Earth, because the composition of the atmosphere did change because before there were humans on Earth. And last but not least today, and actually last but the major cause on short time scales, that is a century, here comes us. So again, when you look at the change of the climate system over I would say a day or a couple of days, you look at the weather forecast. When you look at the change of the climate system over a century to 1,000 years, you look at, I would say, the climate change that we are today interested in. But you can look on longer time scales, as I said, and it's the change between ice ages, when you have scrapped, and present warm ages. And that's what you have learned in school, that there has been an oscillation between the two during the Quaternary era. So again, the climate system has always changed. And what is at stake today is to understand how fast the climate is changing because of us, and how does it compare to past climate change, and whether, because of this comparison, we are running a big risk or not. That's the question today. So the question is not, does the climate change? The answer is yes, it has always been yes. The question is the main cause of climate change today is human activities, and where is it susceptible to bring us? That's the question. So the main cause of climate change caused by human beings is here. It's greenhouse gases emissions. A greenhouse gas is something that has been existing in the atmosphere for how long? As long as there has been an atmosphere, that is a couple billion years. A greenhouse gas is just a gas that has the physical ability to absorb infrared, long-wave infrared emitted by the Earth's surface. That's the definition of a greenhouse gas. Human beings have not invented greenhouse gases, nor they have been the first to emit greenhouse gases into the atmosphere. So there have been greenhouse gases in the atmosphere for, again, as long as there has been water on Earth, because the first greenhouse gas in the atmosphere is water vapor by far. And human activities do not change the water content of the atmosphere, not directly at least. It does change indirectly because of global warming, but not directly because of our emissions. Here you have the emissions of the second greenhouse gas in the atmosphere by order of importance, which is carbon dioxide. And you can see these emissions recorded over a century and a half, derived from fossil fuel use and from agricultural activities, basically, because that's the main source of methane, which is also a greenhouse gas. So these gases, again, they have the ability to absorb the infrared emitted by the Earth's surface. And this causes energy to be kind of trapped close to the surface. And when you trap more energy close to the surface, you increase the energy content of the system. And among other things, you increase its average temperature. So the greenhouse effect is something that has been understood 2 centuries ago by Fourier, French physicist, yes, who published in a scientific paper, because scientific papers are a couple centuries old, an article explaining that there was something in the atmosphere that increased the temperature at the surface or close to the surface. And he called that increase the greenhouse effect. About a century and a half ago, 2 other physicists, among which a French again, but also an Irish one, identified the main gases in the atmosphere that cause this effect, water vapor and carbon dioxide. And a century ago, a Swedish scientist, Arrhenius, was the first to calculate the order of magnitude that would follow a doubling of the CO2 in the atmosphere, the order of magnitude of the temperature increase. And that is 4 to 5 degrees. And that calculation was pretty accurate compared to what the modern models give when they are asked the same question. So what you can see here is, again, the increase of the emissions. Now, to kind of answer the initial question, you can see that along that story of a century and a half, we have made tremendous technical progresses all the time. For example, we have begun to produce electricity. Many people on Earth believe that electricity is clean. Well, you see, we have begun to produce clean electricity, or electricity that doesn't cause smoke when you use it, unless it causes a fire, but otherwise it doesn't. And you see that it didn't prevent the emissions from rising afterwards. We have manufactured, actually the Americans have done so, the first computer in 1945, the ENIAC, And as you can see, it didn't prevent the emissions to go on rising. And actually, that first computer was very inefficient compared to the computer that I'm presently using to show these slides, because the first computer, the ENIAC, was absorbing 150 kilowatts when my computer today absorbs 20 watts. So the ENIAC was very inefficient, but the efficiency of computers didn't prevent the emissions to go on rising. Here you have mainframes that become common. Here you have the World Wide Web that appears. Here you have the digital revolution that appears. And as you can see, nothing stopped the emissions from increasing. So you have a first answer to the question, will technology save us from climate change? The answer is no, because it didn't save us in the past. As you can see, we have had plenty of technological progress. My car today is far more efficient than the car I used to, in which I learned to drive. My washing machine today is much more efficient than the washing machine I used not a century, I'm not that old, 50 years ago, half a century, let's say, etc., etc. So when you look at objects taken one by one, all of them are far more efficient today than they were, let's say, half a century or a century and a half ago. And nothing prevented the emissions from rising. So the story must be a little bit more complex than just finding technological fixes. Otherwise, we would have mastered the issue a long time ago. As I said, one of the main gases that we find into the atmosphere to cause the greenhouse effect is carbon dioxide. It happens that the carbon dioxide is an oxide. The dictionary is well made. Oxides have a chemical property, which is common to all oxides. It is that they are very, very stable molecules. For example, hydrogen on Earth is found under the form of an oxide, which is water. And that oxide has remained stable for 4 billion years. So once hydrogen is under the form of an oxide, which is under the form of water, nothing happens to that water, basically nothing happens, and it remains as water. It's the same thing for carbon dioxide. Or I could have said that for iron, for example. Since there has been oxygen in the Earth's atmosphere, let's say 300 to 400 million years ago, all the iron that you could find on the crust, in the Earth's crust, turned into iron oxide. And today, when you look for iron ore, you find iron oxide. You don't find native iron. And it's very stable under the form of an oxide. It's the same thing for carbon dioxide. Carbon dioxide is a very stable molecule, and that means one thing. Once in the air, as long as it is in the middle of the atmosphere, there is no process to remove carbon dioxide. So as long as it's in the middle of the air, it's eternal. The only way to remove carbon dioxide from the atmosphere is to bring that carbon dioxide back in contact with the surface, where one of the two following things can happen to that molecule. A, it can be eaten by plants in a way, that's photosynthesis. So plants are able, with the help of energy, with the help of a photon, that is sunlight, to get that carbon dioxide back on Earth in chemical molecules, organic molecules. And the other way that the carbon dioxide can be brought back, I would say, on the surface, or rather below the surface, is when it dissolves into the ocean. And that's what physicists call partial pressure equilibrium. It means that if the relative concentration of CO2 in the atmosphere is greater than the relative concentration of CO2 into the ocean, the CO2 goes from one compartment to the other, okay? But that can be reverted. If one day we remove CO2 from the atmosphere, part of the CO2 that has dissolved into the ocean will pop up in the air back again, okay? Because it's an equilibrium. The consequence of what I've said is that once we stop emissions, so today we have created a surplus of carbon dioxide into the air. Well, once we stop emissions, 1 century after the emissions have stopped, a small half of the surplus of carbon dioxide that we have put into the air will still be there. 1,000 years after we stop emissions, about 30% of the surplus that we have put into the air will still be there. 10,000 years after we stop emissions, 10 to 20% of that surplus will still be there. It means one thing. It means that the state of the atmosphere that we had in 1800 is lost forever, and that the climate system that we had in 1800 is lost forever. That's what it means. So it means that you will never see back the climate system of the year 2000, and even the climate system of the year 2020 is going to disappear, and you will never see it back. So climate change is actually not a very good expression. We should call it climate drift, because a change is not necessarily something that, one, is advert, and two, that you don't master. Even global warming is not something that I would say brings bad feelings, especially at the end of the winter. Global warming is not something that threatens you a lot, and certainly not in Texas today. So climate drift would be something better suited, because a drift is something that you don't master. You don't have any control on a drift. It is just something that you undergo, and I mean, you have to do with it. And this graph means one thing which is very important. From now on, we will not stop climate change. We can soften it, we can prepare to it, and we should do both. So mitigation is absolutely essential, because we should soften the landing, or soften the fall, to be more precise, but we will not prevent it. We will not stop the motion that has begun. One of the things that is, of course, frightening with this evolution is that it is going to take place over time frames that are way over human life, way over actually a couple of human lives, and most of it way over the time frames that we are accustomed to when we manage anything. So today, the strategy of any elected government, or the long-term strategy of any listed company, is 3 years when you are in good conditions, and 6 months when you are in bad conditions. So it's way too short to be able to correctly address that issue. And that's one of the tragedies of that issue. It is the fact that we try to solve a long-term problem with short-term solutions. The market, for example, the free market, is a short-term solution. It won't work for that issue. It just won't work. Democracies are basically short-term systems. So I don't say that they don't work, because I like democracies. I mean, having a certain amount of freedom is rather nice. But they have a major weakness, which is that they push us in a direction where we don't care about long-term issues. Because of that increase of greenhouse gases into the atmosphere, as I said, you have more energy which is trapped close to the surface, and so the average temperature of the surface is increasing. People focus a lot on the average temperature on Earth, but actually you will see later on that the inconvenience of what is happening right now is not mostly in the temperature change, it's going to be elsewhere. So I know that the media repeat again and again that we raised 3 degrees or 4 degrees, but it doesn't tell anything to anyone because you don't live in an average temperature. You do live in the surrounding conditions, but you also do live in a world where you have to eat, you have to move around, you have to get close, and actually it's on these items that we will also experience adverse conditions, but I will come to that later on. What you can see here is a graph that shows you the average temperature on Earth. The zero here, the reference, is the average temperature that we had in the last part of the 19th century. What you can see is that during the second half of the 19th century, the climate was roughly stable. Then during the 20th century, the average temperature increased by 1 degree, today 1.2. And that increase is already enough to trigger massive fires in California, which is drying up, massive fires in Australia, which is drying up. It's enough to have triggered emigration from Northern Africa to Europe because drought and insufficient food is triggering riots, or even worse. There has been an article published in the Proceedings of the National Academy of Sciences a couple of months ago, explaining that the drought that took place in the Mediterranean basin since 2006, that has a link with climate change, is also linked to the emergence of Daesh in the region. So you see, with 1.2 degrees, you have already consequences which are rather big, I would say, in magnitude. And it's only the beginning of the story, unfortunately. And because of the tremendous inertia of CO2 once into the atmosphere, and because of the tremendous inertia of the ocean in the way the climate system behaves over centuries, no matter what we are going to emit, actually the climate system of the 20 years to come is the evolution of the climate system is already written. So if we begin to decrease emissions from now on, and we should do it, unfortunately, it is not going to change anything in the way the climate system is going to behave for the 20 years to come. Okay, that part of the history is already written. And what you can see also on this simulation is that we are going, of course, to go through the ceiling of 1.5 and even 2 degrees, which are, I would say, the upper limit that we shouldn't go beyond in the Paris Agreement. We will go beyond. Unfortunately, we will go beyond. And a political promise, as you probably know, only binds those that believe in it. So there has been in Paris the political promise to limit global warming to 1.5 degrees. That promise is not going to be kept. And the promise of keeping the temperature below 2 degrees is not going to be respected either. Okay, these two promises are just fate in a way, unfortunately. I'm going to go now into the consequences, but one of the things that you must already have in mind is that there is no linear relationship between the temperature increase and the magnitude of the consequences, of course. If I take your own body, and if you have an increase of your internal temperature of 1 degree, you're a little sick, but it doesn't even prevent you from listening to this conference. Okay, you feel uneasy, but it's okay. If your internal temperature increases by 5 degrees, you do not miss five conferences, you're just dead. So there is no linear, it's not 5 times as bad as 1 degree. Okay, it's exactly the same thing with the climate system. It is packed up with non-linear phenomena, and so a couple degree increase is not going to be a couple times, I would say, more adverse than a 1 degree increase. Maybe 100 times, 1,000 times, 1 billion times more damaging. This is the way Northern America can be described today when you look at the ecosystems that exist. If you do not clear them to put something else, cities, crops, or shale oil wells, whatever. What you can see is that today the internal part of Northern America is rather dry and sometimes hot, so you do not have thriving ecosystems. But all this part of Northern America can host, I would say, rather nice ecosystems and rather rich ecosystem with plenty of forests. And if you clear the forest, plenty of nice crops. This is Northern America 20,000 years ago. So that is basically 18,000 years before Mr. Jesus Christ was born. So as you can see, it does not resemble what you see today. The first thing is that you have a huge ice cap, under which the Canadians are buried. So that you do not have tar sands. You do not have a problem with tar sands. You do not have the oil pipe Keystone, which triggers a huge debate because there is no oil to be sent from Canada, no Canada. And actually you have the same ice cap, or not the same, but another ice cap, which exists on the northern part of Europe and the northern part of Siberia. And in order to build this big ice cube, you need to remove water from the ocean. And as the ocean floor is at the same place, the level of the ocean is 120 meters lower to what it is today. So you cannot eat clam chowder in Boston because Boston is not on the seashore. It's in the middle of the hills. No harbor and no pier to go and wander at night. What you can also see is that most part of the continent, which is not buried under ice, is pretty dry and cold. Here you have desert, here you have dry grassland, where today you have forests, and you have taiga-like here ecosystems, which today are in the northern part of Canada. Okay, so the ecosystems do not thrive as much, and actually, if human beings lived at that time, they could not grow crops as they do today in that part of the continent. Well, when America went from the state on the left to the state on the right, obviously it happened in the course of a global warming. That global warming is the one that took place before the middle of the last ice age and the beginning of the warm period that happened 10,000 years ago, and that allowed human beings to settle and create agriculture, then cities, then the MIT. Okay, so you are the remote descendants, as I am, of a stable climate that spanned over 10,000 years and that allowed us to improve the way we live in places where the climate, therefore the surrounding conditions, stopped to change. The warming that took place in order to bring the continent from that state to that state is only a warming of 4 to 5 degrees in 10,000 years. Okay, so you can see how much it changed the continent. And actually, exactly the same thing happened in Europe. For those of you that come from Europe, I'm sorry, I do not have the map for China or elsewhere in the world, but as you can see, same thing. Europe 20,000 years ago had a very different aspect from what it has today. And the warming that went that took Europe from this stage to this stage is only 5 degrees in 10,000 years. Now, before I go on, one thing that I can say right now is that a warming of 4 to 5 degrees in a century basically is going to bring war and turmoil and chaos everywhere. That's basically what it's going to bring. So a world that warms by 4 to 5 degrees is not a world where your major problem will be to have aircon so that you don't die or suffocate in the summer. It's a world where you will thrive for stability because it's going to be war and turmoil everywhere. Democracies will collapse, among other things. Here is the first graph. I'm sorry, I always make a mistake. It's not Camila Mora, it's Camilo. I should correct that. I will do it before I send the slides. It's a map that has been released in Nature a couple of years ago, 2018, I think, 2017, I don't know, where with a model, people have computed the number of days in a year when you cannot go outside because you die. Why cannot you go outside and die? It's because you live in a region where it's hot and it's wet. And namely, you have air which is saturated with humidity. And so when the temperature is over the temperature of your skin, which is roughly 35 degrees Celsius, you cannot cool your body through heat transfer because the temperature of the air is over the temperature of your skin. And you cannot cool your body through sweating because the air is saturated with water vapor. And so you die of hypothermia. As you can see, 2 to 3 billion people live in places where the number of days during which you will not be able to go outside without dying will be over, let's say, half the days in a year. And sometimes it's all year round. Of course, this is not going to happen. This is not going to happen in a world where people peacefully wait to be killed. They will move around, and they will move to places that are nearby, and people will fight, and so and etc. So obviously, what you can see here is that this is going to be a cause of major instability because of major immigration. Among other things that the climate drift will do is that it will change the water cycle. Basically, in a climate system which is much warmer, you have more evaporation and therefore more precipitation. But it is not going to be evenly distributed, neither geographically nor, I would say, around the year. You will have more intense precipitation events, but you will also have longer drought spells in a number of places. And the resulting effect in all the mid-latitude countries, namely the places where you grow cereals today, is that the soils will become drier. And if the soils become drier, of course, the crops will not thrive as today. And this will happen also in a time where all that we have used today to increase the yields of crops, tractors, and fertilizers will also be harder to find because of the fact that oil is going to be harder to find, and I'm going to explain that later on. The funny letters that you have here represent actually the greenhouse gases emission scenario. This is the Paris Agreement, basically, and this is as long as we have coal, we burn it. That's basically the idea. Here you have a graph that has been released by the IPCC 1 year ago, or 1.5 years ago, in a special report called Climate Change and Land. And actually, it's the bar on the right that I'm interested in. The color code on these bars is that when it is yellow, you have isolated effects and sometimes reversible. And when you go into the purple color, it means that you have widespread effects and non-reversible. What you can see is that beginning at 2.5 or 3 degrees of global warming, regarding food supply instabilities that trigger riots, at 2.5 degrees, they become widespread on Earth. So again, people will lack food. Greenland has begun to melt. It has begun to melt because the surrounding temperature is too often too high. And as you know, when the ice goes over zero, it melts. Or where the surrounding temperature, to be more precise, because the ice is always at zero, but when the surrounding temperature is over zero, it melts. This melting is bound to continue for the centuries to come, and it is going to add 3 to 6 meters to the ocean level everywhere. The western part of Antarctica, well, Antarctica being centered on the southern pole, you can ask where is the western part, but it's here. So the western part of Antarctica, which is a kind of house of cards of glaciers that all support the neighboring one, is at risk of collapsing if global warming goes over 2 degrees, which it is going to do. Then you have the sea level rise plus the temperature rise of the sea, which is going to attack in a way the ice which is close to the shore, because it happens that that part of Antarctica is on a bedrock which is 1 kilometer below the sea. So the ice cap is thick enough so that the ice sticks to the bedrock, because you have 1 kilometer of ice below the sea, but 2 kilometers of ice above the sea. But the fact that the bedrock is under the sea gives way to the sea licking the ice at the bottom and infiltrating between the ice and the bedrock, and eventually triggering a kind of collapse of the house of cards. Here you have a risk of getting 6 meters extra to the ocean level. So in a couple centuries, you risk 3 meters here, or plus 6 meters here, plus dilatation of seawater. So it might happen that in a couple centuries, most of Florida will be underwater. And we have the finger on the trigger today, Of course, it's going to take a couple centuries to happen, but it is today that we decide whether it's going to happen or not. Today. Economists have looked at climate change for a very long time, trying to figure out how much could it cost to damage the climate system. So maybe I'm going to disappoint a number of people that listen to this talk, but the answer is you cannot say. Why cannot you say? Because by convention in economics, all natural assets are free. As you may know, in economics, all that you count is human labor and human rents. Nothing is, there is nothing for nature. For example, it is essential today that you have 20% of oxygen into the air to breathe so that you stay alive and so that you can produce something. There is not a single accounting nowhere in the world where you have something for this 20% oxygen into the air. But if you remove the 20% oxygen into the air, everybody dies and all the GDP vanishes. But nowhere in the GDP you will find the fact that you have 20% of oxygen into the air. You will find nowhere the fact that you have an ocean. You will find nowhere the fact that you have soils, that you have mountains, that you have rain, that you have 30 million species. This is non-existent into the GDP. And among other things, the climate system is nowhere into the GDP. Now, if an asset is free, how much is worth a damage to that asset? Zero. By convention, it is worth zero. So all the economic models that try to assess how much could cost the damage to the climate system, actually, they are all based on reasoning, which is this. It is all they do. Actually, they are tautological models in which you find at the end the hypothesis that you have put at the beginning. So if you decide that it costs a lot, at the end, you will find that it costs a lot. If you decide that it costs nothing, at the end, you will find that it costs nothing. Nordhaus, for example, decided that it would cost not much. So he concludes that it will cost not much, and he gets the Nobel Prize for that. Yeah, well, it's a long discussion to know whether there should have been a Nobel Prize in economics, but which is closer to cooking recipes than to a science. But so that there it's, I would say, if you stick to facts and to the convention, you just cannot give a cost to climate change. But still, I have brought this article that I find funny because it has been written by people who are researchers in Chicago, in the same university where the market, the theory of free markets and the benefits of free markets has emerged. So I find it funny to say that these people have found out, but it's not worth more than any other conclusion. These people consider that the cost of climate change is anywhere between $10,000 to $600,000 per ton of carbon that we emit. Today, the average American emits 6 tons of carbon per year, 6 tons of carbon. That is close to 20 tons of CO2, which means that the average American costs $60,000 to $3,600,000 per year for the damage that his emissions are causing to the climate system. In other ways, each year, the average American is causing damages for a cost which is 1 to 60 times the GDP per capita in the US. So if you believe in this article, there is only one conclusion that we should draw from the figures that we have here. It is sound economic reasoning to stop producing anything tomorrow morning, because you need to emit CO2 to produce anything. So what this article says is that actually when you believe you get richer, you get poorer. If we want to contain climate change, I would say to the lowest possible consequences, you have here a graph which is going to give you the rule that we should follow. This graph is actually giving you, I would say, a simplified view of the simulations that go from 1890 to 2100, depending on the amount of greenhouse gases that we emit into the atmosphere and the pace at which we emit them. what you can see is all these graphs basically follow the same line. They all follow the same line, basically. And that line is a kind of linear response of the cumulated amount of CO2 that we'll put into the air between pre-industrial times and 2100. It's a linear response of that cumulated emissions to the average increase that we will get. In other terms, you just have to look at the overall amount of CO2 that we will put into the atmosphere, and that's due to the very long lifetime of a CO2 surplus into the atmosphere that I've explained before. So it is acceptable to reason in terms of carbon budget, just the overall emissions that we will put into the air. And that is going to give you the temperature increase that we will get in 2100 compared to pre-industrial times. At the end of 2018, because of coal, oil, gas, and deforestation, that is slashing and burning wood in order to make room for crops, we had emitted, well, we, not just the people that listen and me, but humanity as a whole, had emitted above 2,000 gigatons of CO2. And so we are already committed to 1.5 degree of temperature increase. It's the graph that I showed before, no matter what we do, because that temperature increase is already embedded in a way in the past emissions. So the 1.5 degree of the Paris Agreement is already dead. We can say that we are going to contain climate change. Companies can boast, Microsoft can boast the fact that it's 1.5 compatible. Microsoft is just boasting that it's going to be compatible with something that will not exist. We can discuss whether it is something of great interest to be compatible with something which is not going to exist. I take the opportunity of mentioning that company to recall one thing that has just been published in the Financial Times 2 weeks ago. There has been a survey performed by the Stern School of Business of New York University, looking at the fraction of the directors of the Fortune 100, so the 100 largest companies in the US, the directors of the boards of these companies, that is 1,200 people roughly. That study looked at the credentials that these people had, or have rather, regarding climate change and energy. And they found that 1% of them have credentials in energy and climate change. And the journalist that wrote the article asked the following question: what are worth the commitments taken by companies in which the directors are basically ignorant about the problem? And the answer is, of course, it's not worth anything. And it's the logical answer. It is not worth anything. If we want to limitate the warming to 2 degrees, then you go the other way. It means that we have to limitate the emissions to, the cumulated emissions, sorry, to 3,000 billion tons of CO2, of which 2,250, to be precise, had already been emitted at the end of 2018. And at the end of 2020, we are probably close to 2,350. So we still have a carbon budget, so to say, of a couple 100 billion tons that we should divide among 8 to 9 billion humans for 80 years, for the 80 years to come. And that's all what we have if we want to limit the global warming to 2 degrees. When our ancestors, close ancestors, parents, grandparents, had 3 times that budget for a population that was roughly 3 times less numerous. So basically addressing, it's what I'm going to explain later on, addressing the climate change issue is going on a huge diet. And even though Mr. Gates is very optimistic, technology will not be enough to prevent us from going on a diet. Now, the good thing to know is that we will go on a diet anyway, even if we don't want, because the Earth is a finite system, and the diameter of the Earth was 13,000 kilometers 2 centuries ago, and it is still 13,000 kilometers today. And in 2 centuries, even though Elon Musk dreams of the opposite, it will still be 13,000 kilometers. It's not going to change. If we want to be serious about climate change, we have to divide the world emissions by at least 3 until my kids are my age. So by the time my kids are my age, 30 years, the world emissions should be divided by 3. If you put that in the form of compound interest, it means that the world emissions should decrease by 5% each year from now on for the 30 years to come. And it happens that 5% is roughly what the emissions have done, a 5% decrease, in the year 2020 due to COVID. So basically, addressing correctly the climate change issue is, I would say, putting on a brake, which is an extra COVID each year. That's what it means. If we don't do that, we'll have the adverse consequences that will grow, and that will, of course, one day prevent human societies from growing. So perpetual growth is not going to happen, whatever way you take it. Now, if we have to divide emissions by 3, where do we have to act? Here you have a pie chart of the world emissions not last year, but in 2019. About 20% of the world emissions come from coal power plants alone. Coal power plants actually use coal to create heat. From that heat, you create water vapor under pressure, and that is used to put a turbine in motion, and following that turbine, an alternator which generates electricity. You can generate heat, of course, with gas, and you can generate heat with nuclear reactions. All this is the same principle. You generate heat, and then you create electricity. Coal power plants alone, so they generate 20% of the world emissions. Then you have gas power plants and fuel oil power plants, but mostly gas power plants, that create 7% of the world emissions. That's all gases included in that pie chart. I've included methane, nitrous oxide, and halocarbons. All the gases are included. So electricity production from fossil fuels is responsible for more than a quarter of the greenhouse gases emissions. And of course, here you have the debate on whether we should replace that by nuclear, by renewables, first renewables, then nuclear, first nuclear, then renewables, etc. This is the debate which is taking place here. 7% of the world emissions is cement production. Cement production consists in breaking the lime molecule in two, and one of the two parts is CO2 that goes into the air. And in order to break that molecule in two, you need massive amounts of heat, which is generated with coal, oil, or gas, which also creates CO2 emissions. 10% of the emissions are caused by the rest of the industrial processes, and those are basically blast furnaces in the steel manufacturing, which cause 4% of the emissions, boilers in the chemical industries, and in other material and non-ferrous metals. And then I would say mechanical work is much less intensive into emissions. So when you want to turn steel into a screw, that requires much less energy and emits much less than manufacturing or creating the steel from iron ore in the first place. 5% of the world emissions come from the boilers of buildings. Buildings are not heated everywhere in the world. For example, if you live in San Diego, you don't heat much. And if you live in Singapore, you don't heat much either. 14% of the world emissions are transportation. 6% comes from cars, 4% from trucks, 2% from boats, and 2% from planes before COVID. Now it's less. And so you see, for example, that coal power plants alone represent a bigger issue than cars. Of course, we should deal with cars, especially in the US, where they are much too heavy. But still, we here have an issue which is a little bit lower than this part, this slice, I would say, of the pizza. 20% of the emissions come from agricultural processes. Here you have methane, which is emitted by cattle. You have 1.5 billion cows on Earth. Eating less meat is, of course, something which is useful to decrease emissions. You have methane coming from rice paddies, and you have nitrous oxide coming from fields following the fertilizers or following the use of fertilizers. 11% comes from deforestation. Deforestation is something that takes place in all countries where you clear forests in order to grow crops. So that happens today with soy, that happens today with palm oil, that happens today with, I would say, everywhere the population grows. And Western countries import deforestation every time they import crops that come from these countries. And then you have other processes, such as, for example, waste management. You have methane that come from landfills. You have also special gases, halocarbons, that come from cold chains, etc. So you see, emissions come from a little bit everywhere. And again, if we want to be serious about climate change, we should divide this by 3 in the 30 years to come. Now, technology is more or less useful depending on where you look. If you want to replace coal power plants by nuclear power plants, indeed, technology can play a huge role. If you want to remove the 20% here, it's not a matter of technology. People have to eat less meat, and we have to try to have a world population that doesn't grow too fast. That doesn't have to do much with technology. It's cultural schemes, technology. Here, it's a mix of technology and I would say biology. As we are animals, we like to get out of our homes and like to get out of our offices, because a place that you cannot get out of all day round is called a prison, and you don't like that. And it happens that for as long as we have kept statistics in France, for example, people have moved around 3 times per day for the last 60 years. And it's the mode they use which can change. So, for example, technology will not change the fact that we are animals that want to get out of the cave and that we want to move around. But technology can play a role in making more efficient cars. But technology doesn't play any role in the fact that you can prefer riding a bike than using a car. So you see, technology can play a role, but it is not going to occupy all space. That is not true. And I'm going to conclude this talk with a little rule of 3, showing that it is just not possible. 2/3 of the emissions come from energy. So now I have to talk a little bit about energy. So basically, it comes from oxidizing carbon, which is, I would say, the sophisticated way that we call combustion. And so this is burning coal, oil, and gas, which is causing 2/3 of the emissions. So why do we do this? Why do we use energy? I am sure that if you go out in the street and ask to the first people you run into what is energy, you will get anything but the correct answer. One of the answers that you might get is, and especially in Texas today, is energy is a bill. It's something that you have to pay, and it can increase a lot in bad times. Actually, this answer is a wrong answer. It's always a wrong answer. It's a wrong answer because when you look at what energy costs to human beings compared to all that they earn, you will realize and come up with the conclusion that it costs a couple % of what we earn. Actually, the accumulated price on Earth of buying coal, buying gas, and buying oil is 5% of the world GDP. So it is a small bill. And if you look at energy as a bill, you are going to devote to energy a small fraction of your time, because if it is a small cost, you don't need to care a lot about it. And actually, if energy was not 5% of the cost, but 99% of the cost, I can bet that the credentials in energy of the directors I've just mentioned before would not be, there would not be 1% of the directors with credentials regarding energy, but 99% of directors with credentials regarding energy. So the fact that there is already 1% is precisely because of this, is because when you run a company, you don't care about something that doesn't cost much. If I look, for example, at the train operator in France, SNCF, which is the first consumer of electricity in the country, consumes 1.5% of the electricity produced in France. And it is one of the first consumers of oil products because we have trains that are powered by diesel oil. Energy costs to SNCF only 3% of its earnings. 3%. Nothing. I mean, trade unions are a bigger menace for the profits of SNCF than the cost of energy. Okay. But actually, this reasoning is as sound as if I said, okay, your brain is only 2% of your weight. So you should care about your brain 2% of the time, for example. It's far enough. Actually, of course, your brain is 2% of your weight, but 100% of your body depends on the fact that your brain is in good condition. Actually, it's the same thing for energy. Might cost us 5% of what we earn, but 100% of what we earn depends on the fact that there is energy. 100%. So it is not a good answer. The second answer that you might get today, especially in Europe, is energy is something to be saved. Actually, energy is nothing that it has never been saved. Here you have the energy consumption or the energy use, because actually energy consumption is not a proper term, because you don't consume energy by yourself, you don't drink oil, and you don't eat coal, and you don't breathe gas, and you don't put your fingers into the socket. I strongly do not advise that you do so. So actually, you do not use energy. I will say later on what is basically consuming energy. But the energy use on Earth has never stopped to increase. So there has never been something as savings on a large scale. So no savings. Something else that you might say today, what is energy? It is something that is going to be 100% renewable. I've got good news for you. 100% renewable is no big deal. We have done that for all historical times before 200 years ago. Since the apparition of human beings on Earth until 2,000 years ago, the world has always been 100% renewable. Always. On this picture, you can see, for example, a renewable boat made of renewable wood, with a renewable person pushing a renewable stick in order to put a renewable motion in place on a renewable river. You have renewable air that might power somewhere a renewable windmill, and you might have downstream a renewable watermill, and you have here renewable wood that is going to give renewable energy in that castle, and you have a renewable horse, which is enables to have renewable ground transportation, eating renewable grass. All this is renewable, okay? So having 100% renewable world is no big deal, no big deal. It is feasible. It has been done for all the times. Now, the good question is, why, how come that we have mastered renewable energies for so long? How come we had to wait for this in order to build an industrial civilization? If it were so easy to keep the industrial civilization with only this, how come the industrial civilization did not emerge when we had only this? How come? This is one of the questions that I ask my students for the termination exam that I give them at the end of my course. Okay, one of the questions. Please do explain why we had to wait for fossil fuels to trigger an industrial civilization. And actually, the answer is physical. If you put 1,000 cubic meters of air through this windmill, you are going to get the same energy content than when you get 3 milliliters of oil from this. So and this, you can transport it everywhere. You can use it whenever you want. When here, you have to wait for the wind to blow in order to have flour into your windmill. And you can store flour. So with flour, you can do it. With electricity that you cannot store, because electricity is by definition an electron in motion, and you cannot store an electron in motion unless in supraconducting material, but otherwise you cannot. So we had to wait for this because basically the energy density of this is far greater than the energy density of this, and it makes all the difference. So the bad news is that you will never keep an industrial civilization going back to this. It is just not possible. It is just not possible. So all these are bad answers. And actually the good answer, I'm not going to give you the physical answer. This is the good answer. Energy is Iron Man for real. That's what it is. Because energy is the food that can power all the machines that are the left finger, the right arm, the left elbow, the right arm, the left foot, and the right knee of Iron Man. This is the left finger of Iron Man. It can pull tons of load that you wouldn't be able to pull with human beings unless you put hundreds of thousands of them to do the same work. Here you have machines that are the left foot of Iron Man and that are able to knit clothes much faster. This machine replaces hundreds of people or thousands of people that would knit clothes. The machines build cars, themselves made of steel that have been manufactured in Iron Man's mouth, let's say, and that you couldn't manufacture with arms and legs. This truck is as powerful as 4,000 pairs of legs. This steel mill is as powerful, is it a steel mill here? I don't know, or glass mill, whatever, is as powerful as 10 million pairs of arms, 10 million pairs of arms. This satellite sees much farther than your eyes, etc. So energy is the food that is able to power all this fleet of machines, the machine that surround us everywhere, and that has turned us into Iron Man for real. Only you do not have a costume that you put on in the morning, you know, that does click, click, click. But just the fact of eating bread and butter in the morning has put in motion this machine, because you may have a mirror to wash your teeth after you have taken your breakfast. This machine, because you had to build all the plants in which the bread was processed and the crops were processed, etc. You have used all these machines and you do not realize it just by putting bread on butter in the morning. You have used all of them, okay? If you looked at the combined power of all the machines that we have today on Earth, so at the time I'm talking to you right now, we have all these machines that are working for us everywhere on Earth. And these machines with their special food, which is oil, gas, and coal, and marginally the rest, nuclear, hydroelectricity, etc., they have multiplied the muscular power of humanity by a factor 200 on world average, and 600 for a European average, and 1,000 for an American average. So your standard of living today, I'm sorry to say, is just as if you had 1,000 slaves at your service all year round, all day round. That's what it is. If we didn't have energy on Earth today and therefore didn't have machines, the world GDP would be divided by a factor 50 to 100. The world GDP would be divided by a factor 50 to 100, because today production is not coming from human beings, it is coming from machines. And this is why all the economic models fail to account what is happening today, because they do not include energy and machines. They still believe that the first limiting factor of production is human beings. Nonsense. You have excess of human beings everywhere, you have unemployment everywhere. So it's not a limiting factor if it's in excess. So this is why economic models fail, is because they do not stick to the physical reality that production is today done by machines, and these machines, they use energy. It's their food. And the consequence, the logical consequence of what I've just, and so you don't consume energy, the machines consume energy. And when you say that you consume energy, actually you must remove that expression, get it out of your heads, and replace it by master a fleet of machines. So consuming energy is mastering a fleet of machines. That's what it is. It is becoming Iron Man. And here you have a linear relationship, which is a logical consequence of what I've just said, between energy use, which is the size of the fleet of machines, of active machines. So it's the size of your Iron Man costume. And here you have the GDP in constant $billion. So macroeconomics is as simple as a straight line, as simple as a straight line. I've discovered this relationship by luck. One day, let's say 12 or 13 years ago, I decided to plot the GDP against the energy consumption to look, to have a look at what it might be. And I found that this, and year after year, still goes on. And when you look at some specific countries in which the GDP is dwindling today, you find that these countries are under energy stress, like Greece, Italy, Spain, etc. So what this graph tells you is that energy efficiency has been active, but at a very slow pace because basically energy efficiency makes this curve a little convex. Okay, it makes this curve a little convex, but it is a little convex. You do not have anything that resembles decoupling on this curve. Absolute decoupling. Absolute decoupling would be a curve going like this. We've been trying very hard for a couple decades and it is not happening, and it will not happen for physical reasons. And that's the predicament of climate change, because most of this energy is fossil fuels. Because most of this energy is fossil fuels, and because actually industrial revolution was getting rid of renewable energies to replace them by fossil fuels. Here you see that basically the world GDP is following the world emissions. So it's what I just said before. You will not get back to this point regarding emissions while the GDP even remains constant. This is not going to happen. This is not going to happen. And the reason why it might surprise a number of you is just because the GDP today is not taking into account natural resources and our dependency on the environment. That's just the reason why. So basically macroeconomics are false from beginning to end. So you can set up a Nobel Prize for a false science. You can do it. You can establish peer-reviewed literature for a false science, which is done. But basically, I mean, this is very obvious. And when you look at oil and GDP, I would say they are just even better. Here you have a curve, a red curve, same thing. I discovered this by mere luck, but then I found the explanation. The red curve is the year-on-year change. Actually, it's a 3-year moving average, but the year-on-year change of oil production in the world. It's oil production, therefore oil consumption, because you have very limited stocks on the Earth's surface. And the blue curve is the year-on-year change of the world GDP of the average GDP per capita in the world. What you can see is the two adjust very well after the oil shocks, therefore after the period when we got rid of all the easy savings that we could make. And now you can also see something which is very interesting, which is that you have a small lag between the variation of oil production and of the GDP per capita. And that lag is in the way first oil changes, then the GDP per capita changes. So it's not that we get richer because GDP comes from Mars. Maybe it's because GDP comes from Mars that Mr. Musk wants to go on Mars, wants to find the source of the GDP, or the source of growth, rather. No, it's not because you have GDP growth coming from Mars that we get richer and buy more oil. It's because we have more energy, therefore a bigger fleet of machines, that we produce more and have a bigger GDP. Actually, counting the GDP, counting the energy in kilowatt hours, or counting the GDP in dollars is basically counting the same thing with two different units. That's basically what it is. Okay. So the party that we are in right now can be summarized in one slide. We have fossil fuels below the ground, which are free because the formation of fossil fuels is free for everyone. You did not pay a single cent for oil to exist. Okay, GR in Dallas did earn a lot of money with oil, but he did not create oil. He just had the good luck of sitting on the oil and deciding that it was his, but he didn't create oil. The creation of oil is free, as is the creation of wind. So when people say wind is free, so we should take advantage of free wind, yes, but oil is free because the formation of oil is free also. So we should take advantage of free oil, which is what we did. So oil, as coal, as gas, they burn, so they can allow us to power machines, and these machines are going to allow us to transform all the rest that we find on Earth, from whales to stones, and they allow us to produce objects, and actually these objects are only natural resources that are transformed by machines. That's what they are, natural resources transformed by machines. Because of the tremendous productivity of work that has been added to our arms and legs, when we say that the productivity of work is increasing, it's not because like Shiva, we have now 42 pairs of arms and 53 pairs of legs. It's because we have an exoskeleton of machines that manufacture for us. And productivity, when the productivity of work increases, it just means that you have more machines per person. It just means this. And because of the productivity of work increase, we have more free time because machines work for us. And that free time has been devoted to creating service jobs that you do not have in a world of scarce energy. In a world of scarce energy, people are busy growing potatoes and chasing animals. They do not become consultants as I am, or professors or whatever. We have plenty of leisure. We can go on holidays, go off during weekends, stop working after we have worked 40 hours in the week. We can retire, we can pursue long studies before we work, etc. All this is allowed by machines. So if you can do a PhD, it's thanks to machines. Otherwise, you couldn't, and I couldn't do my job. Because of machines, people do not need to be in the countryside anymore because machines work for us in the countryside. So people can gather in cities. You can look in the world. Cities grow in countries that increase their energy consumption, therefore their fleet of machines. You don't have large cities or large, I would say, rich cities where people have things to do and do not just live in slums. That requires a lot of energy and a lot of machines. When China accessed to energy, urban emigration began. It's also true for the information society, globalization, which requires a lot of transportation, therefore a lot of oil, etc. So all that we have witnessed for the last 2 centuries is due to one main process, the increase of the energy supply, therefore the fleet of machines. Now we have 2 limiting factors. The first one is that it takes 50 to 400 million years to form this. So it's not renewable in the course of historical times. And mathematics tell that when you draw from a non-renewable resource, the extraction curve can only follow the form of a peak. Okay, it's all it can do. That's a mathematical theorem. I can still demonstrate it. And it's true for oil, but it's also true for copper ore, vanadium ore, aluminum ore, etc. And diamonds, sorry, ladies. So all is going to follow the same curve with a peak for non-renewable resources. And you have a second limiting factor, which is climate change. A big difference between the two is that regarding climate change, all the information is public because it's issued by research labs, and research labs, as you know, by definition, make public all they know. Here, all the information is detained by private interests. So if you want to have, I would say, an opinion in which you are confident regarding what is happening in fossil fuels, it requires 5 to 10 years to discuss with experts everywhere and hope that they will have drunk a little too much and tell you the truth. It is very, very long to get a consistent picture of, I would say, a fossil fuel future from this perspective because the information is private. And in between, we have this. So the GDP is a flow which is created by transforming natural resources with non-renewable energy. So once you've understood that, you understand the predicament of the Meadows team. So it's back to the origins as I speak to people that come from the same place. As you may know, Donella and Dennis Meadows and other people from the MIT 50 years ago issued a report called The Limits to Growth, following system dynamics that they performed in the lab of the MIT, and saying that as long as we seek economic growth, the system is bound to collapse, no matter how optimistic we are on assumptions on the initial stock of non-renewable resources or technological progress. That's the predicament that was issued. Regarding oil, for example, I would say the peak has passed for conventional oil 12 years ago. I'm sure you're not aware of that report. I'm sure not that many of you are aware of that report that was issued by the International Energy Agency, but I knew it much before. In 2018, they issued a report saying that conventional oil, which is all that is not shale oil and tar sands, went through a peak in 2008 and has declined since then. Now, and I'm going to end with this. How can we envision the future in what I've explained? There is a little rule of three that I love called the Kaya identity, which is of great help to understand where we could go. It begins with a tautology, which is that CO2 emissions are equal to themselves, which is so far, I hope you will accept. Now, on the right part of that identity, I'm going to divide and multiply by the energy supply in the world. Here you have a term which is CO2 on energy. And CO2 on energy is basically how much CO2 you have to put in the air to get 1 unit of transformation of the world, because energy is transformation by definition in the physical world. So that's the debate on whether we should replace coal by nuclear, oil by gas, etc. Then I'm going to divide and multiply by the GDP. This is a unit which is energy by unit of GDP. So it's how much you have to transform the world to get 1 unit of added value for something which is more useful than the natural resources it derives from. It is much more convenient to eat an egg with a fork or with a spoon than with iron ore. So we like to transform iron ore into spoons because we find it more convenient. That transformation requires energy and provides an added value. Then I'm going to multiply and divide by the world population. And here you have the amount of services per capita. So the amount of added value is a proxy for services, spoons, forks, tables, chairs, and the internet, times the population. So what I've just written is that everything equal otherwise, greenhouse gases emissions are a linear function of the size of the population. So the more numerous we are, the more we emit, everything remaining equal otherwise. It is proportional, it's the curve that I've just shown before, to the production per capita, which is, of course, the debate on can we have absolute decoupling with this increasing while this decreases. Then it's the energy intensity of economies. So if we can use less energy to produce the same thing, this improves. And this is a first term which involves technology. This doesn't involve technology, and this doesn't involve technology. And then you have the last term here, which is the carbon content of energy. And I've just explained before, it's replacing coal by renewables, coal by nuclear, etc. Now, if we want to stick to the 2 degrees, we have to divide CO2 emissions by 3 by 2050. And Will recalls that even if we don't want to decrease CO2 emissions, there will come a day when fossil fuel supply will decrease because of the limitation of fossil fuels. As I said, extracting from a non-renewable stock can only go through a peak and decrease thereafter. So eventually this will decrease anyway. This will decrease anyway. I would say the nice part with an identity is that if this is divided by 3, somewhere here, I must have a combination that allows to have also a division by 3. A first way to achieve a solution is to divide the population by 3. It is not something people consider with much optimism, or rather with much joy. It's not something that I don't know many people that I would say welcome the idea of having 2/3 of their relatives and friends that would disappear in order to solve the issue. When you look at the scenarios that are issued by demographs, they say that the population could increase by 25% in 2050. Now, it's a could, because if we get an extra COVID in 2032, which is as nasty as the Black Plague that we had in Europe during the Middle Ages, well, half the population gets killed, and that's it. I mean, so this is a scenario. It's not a forecast, okay? Beware of not mixing up scenarios with forecasts. A scenario is not a forecast, okay? This is a hypothesis. If we do not have a major plague, it's something which is going to be close to that, okay? But it's not a prediction. So this should be divided by 3, and this increases by 1.25. So obviously, the 3 remaining factors should be divided by 3.75. Okay, that is almost 4. We could divide production per capita by 4. That's a way to solve the identity. Means that the wages of everyone is divided by 4, or are divided by 4 rather, means that the pensions are divided by 4, etc. So it's a way to solve the issue. You will not find a single economist advocating for that. Not that is right, and not that it's going to happen, just that it doesn't want to believe in this option. And all the economists tell you that we have long-term growth, which is the biggest joke I've ever heard. So we have long-term growth, and so the GDP per capita is going to increase by 2% per year. You will have noticed that lately it has not been the case, but it doesn't prevent these people from believing that it will resume. Compound interest make it so that if you increase something by 2% per year for 30 years, you get the multiplication by almost 2. So if we believe in this scenario, and if we believe that we can have growth, it is a can and not should, a can, then these two terms are multiplied by, let's say, 2. When this should be divided by 3. It means that technical fixes should do the job of dividing the combination of these two terms by 6. We agree? It's a rule of 3, very simple. Can we divide the energy intensity of the economy by 6 in 30 years? By 6 in 30 years. Well, we can look at the resume of the people that would apply for such a job. And we can see that actually what this person could boast is a decrease of a little bit over 10% in the last 2 decades. Okay, so we can hope of something like 30% less in the 30 years to come. And among that 12%, sorry to go into details, but one of the causes of this gain is inefficiency is not the fact that we had physical efficiency, it's the fact that we had false GDP coming from the inflation of assets. You may have noticed that the cost of real estate, that the cost of shares, that the cost of the Bitcoin, everything that can be traded, and the cost of art has just skyrocketed for the last 2 decades, and especially for the last decade, thanks to quantitative easing. And that creates false GDP, which is not discounted when you calculate the GDP for real. So part of this is a fake. It is not true efficiency that you had in cement manufacturing, steel manufacturing, car manufacturing, etc. So this is not going to do the job by itself like this. And now you can look at the carbon content of the energy because of the renewable boom, etc. And so what you can see is that during the last 2 decades, thanks to the renewable boom, no, actually thanks to nothing, we had almost 0 during the last 2 decades. Actually, the trend of decrease, slow decrease, was faster before the renewable boom than after. That's because the nuclear boom was far more efficient, and switching from coal to gas in part of the electricity generation was also more efficient. So what you can see here, and actually the major decrease in the CO2 emissions in the United States for the last 2 decades is due to the shift from coal to gas in power generation. That's the main cause. And it has nothing to do with Obama or Trump or whatever. So you can see here that it is very unlikely that the combination of these two is going to divide these two terms by 6 when we have a rising population and rising GDP per capita. What we could have, if we want it, but fasten your seatbelts, we should work on a slower increase of the population. So the first thing, which is very useful if we want to mitigate climate change, is to deal with limiting as much as we can, with, of course, peaceful methods, the increase of the world population. Peaceful methods are, for example, women education and women empowerment, social systems, things like this, which is not technological fixes at all. at all. It's not a technological fix which is going to convince a woman that it's desirable to have less kids. Not a single minute. We could accept a decrease of the GDP, a slow decrease of the GDP per capita. Today, anyway, we are economic obese. We eat too much, we drink too much, we drive too much, we have cars that are too big. I mean, so it's not going to be very painful. Actually, it's going to be rather useful if we do this. Of course, if we want to be communist in the world, so that at the end an Indian has the same GDP per capita than an American, it's rather division by 4 to 6, 4 to 5, etc. in the US. But still, we can remove a significant fraction of the GDP, and it's not going to hinder our living conditions, really. It's going to hinder our social status. It's going to hinder a number of things, but not really our way of living when you think about it. So the challenge here is the transition rather than the final state. And it's not going to be, technology is not going to be of any help. This is psychology, sociology, desirable model, etc. It's not at all an issue of technology. This is an issue of technology, and if we accelerate, we could reach, but we have to decide that it is the first objective of the economy, the first, okay? Not having companies that are valued 1 billion in the NASDAQ, okay? No, that's not an objective. We should have this as the first objective of the economy. We can probably achieve 1 to 1.5% per year in engines, etc. And if we are really willing, we could achieve something like 2% per year, which, for example, means that each year in the world, we replace 80 coal power plants by nuclear power plants. Okay. In the US, you have a little below 100 nuclear reactors. So it gives you an idea, an order of magnitude. So basically, you should duplicate the nuclear fleet of the US each year. Okay. If we do all this, then we meet the challenge. So this is the end, or actually the end, not the end like in Jim Morrison's song, but it's the end of my talk. I hope that you discovered a couple little things during this talk regarding the magnitude of the challenge. And this challenge, we can address it, or we can just submit the consequence. I would say suffer because of the consequences. This is a statue of Confucius, you know, an ancient Chinese, I don't know, philosophist, so to say. And among the things that he said that we can become wise by 3 ways. The first one is to think, which is the best one. So I hope that you will accept to think. The second is to follow those who have thought, which is imitation. But then you have to trust people without wanting or pretending to understand. And the hardest way to learn is by experience, which is try and see where it leads you. But when you're in a race against the clock, it is the best option to fail. So my advice is think first and encourage everyone to think first, which is the thing that we are not doing today. The thing that we are not doing today. And the second thing that he said that today, basically, we do the reverse of what he advised. We adjust the action steps to, we adjust the goal to the action steps. It would be too hard to act, so let's not act. But as I've explained before, not acting is not going to prevent from suffering. It just guarantees the fact that just a little later on, instead of solving the issue will solve us in a way. okay, the solution will be in collapse, unfortunately, because we live on a finite planet. Might have been a little long, but then I'm open for questions if there is any question. Thank you.
Thank you very much for your presentation. That was very insightful and yeah, very complete. Everyone who wants to stay right now can. We went a bit more than the time we decided at the origin. However, we're gonna ask and answer some questions here right now. When we're looking at the Q&A, we can see several questions about geoengineering and also carbon removal technologies. So Jean-Marc Jancovici, what would you have to say in a few words about carbon removal technologies and also solar geoengineering?
Carbon removal technologies, basically you have something which is very efficient and very old, which is called trees. So the best carbon removal technology that we have is growing forests. If we want to grow forest, we have to recover land that was initially devoted to crops. So basically, if we want to grow forests, we have to eat less meat. In France and in the US, it's the same thing. 80% of surfaces that are devoted to agriculture, both pasture and crops, goes to feed animals. So if we want to capture carbon from the atmosphere, the best thing that we can do is eat less meat. Another thing that we can do is to have agricultural techniques like no tilling, stop plowing, etc., which are efficient to put back into the soil part of the carbon that was removed from the soil when we turn forests into agricultural soil. That the second, well, with forests, this is the best option. People that dream of technological fixes to remove carbon dioxide from the air dream of doing the following. They dream of removing an inert molecule, because as I said before, carbon dioxide is an inert molecule, which is why it doesn't have any chemical process that removes it from the air. They dream of removing an inert molecule from the air, and that inert molecule is present at a concentration of 0.04%. Now, any of you who has done physics or chemistry knows that removing an inert molecule, which is present at the concentration of 0.04%, is going to cost you a massive energy spending. And actually, people that have done a first order calculation came up with the result. I have not checked it up, but I trust it, that it's going to cost about half of the world energy supply to do this. Yes. Something that is the most powerful tool that I know when you want to assess an idea is a rule of three. It is the most powerful tool. And what I tell to my students is that when a good first order calculation leads you to a very different result from a sophisticated model, the only question is where has the model failed to represent reality? But it's the only relevant question. Somewhere it has failed. Of course, you have to have a relevant first order calculation, but geoengineering is the dream of modifying the energy balance of the Earth's climate. For example, former Nobel Prize in chemistry, Paul Crutzen, thought of putting sulfur dioxide in the upper atmosphere in order to create sulfates that will reflect sun ray. My belief is that this is something which is probably more dangerous than a good idea for the following reasons. The first one is that you don't have the time to be sure that you are going to succeed when you do that. It's a bet. We are sure to succeed if we replace coal power plants by nuclear reactors. We are sure to succeed. It's proven. We know how to do it. Okay. you're not at all sure to succeed if you put sulfur dioxide in the upper atmosphere, because it can happen that part of the sulfur dioxide is going to remain there for a shorter period than what you expected. And if you put massive amounts of sulfur into the atmosphere, you will get massive amounts of acid rain. So in order to prevent ecosystems, you are going to kill them with acid rain, which is a very good idea, etc. So, and the last thing is that these fixes, you have to maintain them all the time. And simulations have shown that the day you stop, not only the climate system catches up the warming that you would have avoided in a couple of years, but it adds on the warming that would have happened with the extra greenhouse gases emissions. So basically, the day you stop to put sulfur dioxide into the upper atmosphere because you run out of balloons, sulfur, rockets, or whatever, which eventually you will, then the average temperature on Earth skyrockets by a couple of degrees in a couple of years. And then you kill a significant fraction of humanity. The other dream that would be to put mirrors at the Lagrange point between the Earth and the Sun is also something that, when you look at the orders of magnitude, it's just like Mr. Musk believing that he's going to put 1 billion people on Mars. I mean, maybe he's going to put himself on Mars if he's very lucky, and he's going to be very bored because he cannot even go out for a stroll. But if he really wants to end like in 2001, Space Odyssey, that's his problem. But you are not going to move 1 billion people. So these are dreams. I mean, they are nice dreams, maybe, but we should be pragmatical. And being pragmatical requires to waive or get rid of ideas where a simple calculation, a simple first order calculation, shows that it's never going to work.
I see. Thank you. And when you say it's a dream, you probably also mean because of the lack of energy we're gonna meet at some point in the future.
Yes, of course. Of course.
So regarding that, I have a questions to sum up all the questions I can read. It's as researcher and as a researcher in, for example, in the digital world, or in for computer science, etc. How do we, and also as citizens, how do we adapt to this? How do we adapt our research? How do we adapt our universities to face a lack of energy? How to face the lack of money that comes with the lack of energy, and at the same time produce research for to reduce emissions and adapt to this world. I know there is no answer, but could you give maybe a lead on this?
I'm going to answer a major question before. Yes, my backdrop photo is in the northern part of Brittany, close to the Cap Fréhel, for those of you who know that place. How do we adapt? We adapt by deciding that we work on the topic. It's not going to be easy, and it's not going to be instant. As you said when you read my short bio, I've been involved in this issue for the last 20 years. So of course, I begin to be at ease with the issue. What are the, I would say, things that we should really work on, and dead ends that we should not look at or remove very, very quickly. It's going to take your time, which is the thing that we don't have, but still, it's going to take your time to take a deep look at the issue and to see how you can combine it with the world that you live in today. And there is no other way. It's a complex issue. It's been said at the beginning. We live in a complex world. It's also been said at the beginning. Energy has framed everything that's around us. I've said it, tried to explain it. So you are not going to unknit that complex web in a couple minutes, even in a couple hours, even in a couple days, and even in a couple years. So the first useful thing that you can do is spread the knowledge around. the second useful thing to do is to confront what surrounds you to that special accounting, which is carbon accounting, which gives you a first view on where to act. And we have to learn the grammar, we have to learn the numbers that are associated with this issue, which, as I said, the energy and climate change challenge is nowhere into conventional economics. So regarding the unit that you manipulate all day, which is money, you're blind regarding what I've just explained. You're blind because it has been designed so. I mean, it's not because I'm not being pretentious saying that. It's just that it's been designed so. So the way to go, it's a long journey to go into that issue. It's a very long journey, and all that I hope is that a number of the people that have listened now desire to begin that journey. But it's just like getting rid of the Mordor. I mean, it's going to be as difficult.
I see. Well, thank you for answering those few questions. Oh, I see another questions. Yeah, someone is asking a good source for studying the Kaya identity.
Well, there is a page on my personal website. So my personal website bears my name, Jancovici.com. And there is a page which is called What is the Kaya Identity? And you can refer to that page. It's a little bit old because most of that website was written when I had time, which is now something that I cruelly lack. But I mean, physics are eternal. So even if it's old, part of it is still valid. And you will see, you can go back to this identity step by step. It's also, then when you must, if you want to take deeper looks at the various terms, it's part of the journey that I've just mentioned before. You must look at the demographic scenarios and look at what can change them. Look at to what extent people would be unhappy if the size of their cars decreased a little, etc. So all this is part of the investigation that you have to make. It's not on my webpage, of course, but I can say my webpage can be used as a kind of reminder for where to look.
Oh, thank you for that answer. There's one question also on cryptocurrencies. So I guess it relates very directly with the digitalization of the economics, as we say. Would you have a word on cryptocurrencies and digitalization?
Yes, I'm going to have a word before on the digital economy at large. At the SHIP project, and at least the summary for policymakers is available in English. We have issued 1.5 years or 2 years ago a report on the carbon footprint of the IT system, of the digital economy. Today, if you sum up the manufacturing of all the devices that we use, computers, just like the one I'm using right now, smartphones, servers, networks, because you need components for the network, so and and connected TV screens. So the manufacturing of all this, and you add on top the electricity production to run all this, and electricity production on Earth, I've shown it before, is more than 25% of the greenhouse gases emissions. You come up with the result that in 2018, the digital was responsible for 4% of the greenhouse gases emissions on Earth, which is equivalent to the world fleet of trucks. And it's increasing at 8 to 10% per year, 8 to 10% per year. There is nothing which is less sustainable than the digital economy. And in 2025, at that pace, it's going to be the equivalent of the world fleet of cars. World fleet of cars. 80% of the data flow on the network is video. So what we are doing right now. Actually, when you look at the breakdown of this 80%, a quarter of that 80% is Netflix and the like, because it's point to point and it's much more demanding in resources than one to many that we had before with analogic TV. 25% is porn sites. 25% is YouTube. And 25% is all the rest of animated images, like the video we're using right now, or the video of your little cousin that just had his first teeth, and which, of course, the mother must spread, or the father, the proud mother or proud father must spread around 3 seconds and a half just after. So that's 80% of the data flow on the internet. So the increase of the carbon footprint of the digital economy is basically linked to the increase of the consumption of videos. Again, is this essential to our happiness? Is it essential to our happiness to see, to have a better definition to look at the sex? I'm not sure. Is it essential to our happiness to have a better definition to look at your little cousin having his first teeth? So, but we are digging everywhere, extracting metals, and putting plenty of CO2 into the atmosphere to benefit from this kind of thing. The cryptocurrencies are part of this, a small part today, but it might increase, of this digital system. Basically, they are of no use. Basically, they are of no use. I mean, the benefit that we get from cryptocurrencies that allow to pay a ransom when you get when you are blackmailed, or I mean, what is the benefit? No benefit. So it's among the things that we should waive instantly if we were a little wise.
It's probably a part of also maybe the artificial GDP growth.
Of course.
Growth, yeah, probably. Well, thank you. I think now we've been there for 2 hours. So to end this conference, I'd like to thank everyone for coming here. Thank you, Caroline, for helping me organizing this. Thank you, Jean-Marc, for coming. Last but not least, Jean-Marc, would you have a word for the MIT researchers, students, for, I don't know, for improving their research toward a better understanding for climate change, etc.?
Yes, I will say something. We desperately need wise research, I would say, or relevant research to address this issue, which is probably one of the toughest challenges that we have to address. I mean, finding a way to live a peaceful story for the 80 years to come on a crowded planet is probably among the toughest challenges that you can dream of. So we desperately need all the brains that we can find to be involved into finding part of the solution to that problem. I'm not going to give you silver bullets and say, of course, here is a list of themes that you should know. I mean, you're intelligent people, otherwise you wouldn't have, you wouldn't be doing a PhD in the MIT, so you'll find by yourselves. Again, my advice is first learn, understand correctly the issue. You had 1 hour, sorry, and a half. It's not enough. 20 hours is something which is closer to what you need. And then find by yourself what you could look at in order to be a little part of the solution.
Thank you. Thank you very much. So I think, Caroline, I will leave you the last word.
Yeah, wonderful. Again, thank you so much for joining us, Jean-Marc. That was very thought-provoking with a little bit of humor, but also very sobering, and, you know, introduced some new ways of thinking about things, which is very interesting. And thank you to everyone who stuck with us. I know we went a little over, but I'm glad we got a chance to answer some of the questions and have a little bit of dialogue. And just to, I guess, a logistical question, Jean-Marc, will we be able to share your slides with anyone who's interested?
Yes, you can, of course, you can both share the video.
Yeah.
I mean, you can put it in the public space, and I will send you the slides after I've corrected the little mistake that I mentioned during the talk.
Fantastic. Well, thank you again to everyone. Thank you, Jean-Marc, and I hope everyone has a great rest of their day. Okay.
Thank you very much.
Bye,
and
everyone.
have a nice rest of your life, because I'm not sure I will talk to you
There you
for the
go.
rest of mine.
We
Great.
never know. Yeah.
Bye-bye.
Goodbye,
Bye.
everyone.